In the vast landscape of mathematics, functions serve as the cornerstone for understanding relationships between variables. From the simplest arithmetic operations to the most complex theories of calculus and beyond, they are not mere abstract entities. Rather, they provide a framework for modeling real-world phenomena, making them indispensable across disciplines such as physics, engineering, economics, and computer science. The concept of functions spans from basic algebraic equations to advanced topics like differential equations and even quantum mechanics. In this journey through the world of functions, we will explore how their properties, such as continuity, differentiability, and integrability, form the backbone of calculus. By unraveling these concepts, we uncover not only the beauty of mathematical theory, but also its practical applications in everyday life. Understanding functions is crucial because they allow us to represent relationships between quantities in a clear and concise manner. Whether it's modeling population growth or predicting the behavior of electrical circuits, functions offer a powerful tool for analysis and prediction. In this narrative, we will journey through several key mathematical concepts, ranging from the foundational real number system to advanced topics like implicit differentiation and power series, that highlight the versatility and importance of functions. In mathematics, the real number system forms the bedrock upon which much of modern mathematics is built. It encompasses all possible decimal expansions, creating a set that includes both rational numbers, those that can be expressed as fractions, and irrational numbers, such as or a2. This system's completeness means every non-empty subset bounded above has a least upper bound within R, ensuring the existence of real numbers for any given value. The real number system is represented through various types of intervals: open, closed, and half-open. These intervals are crucial in defining continuous functions and understanding limits. For instance, an open interval AB includes all points strictly between A and B but not including A or B themselves. A closed interval mathematical induction provides a method for proving statements about natural numbers by showing that if it holds for one number, it must hold for the next. This technique is essential in establishing properties of sequences and series, which are fundamental in calculus. The bisection method further illustrates how intervals can be used to find roots of functions. By repeatedly dividing an interval into two halves and selecting the subinterval where the function changes sign, we converge towards a solution. This process not only demonstrates the power of numerical methods, but also introduces key concepts like continuity and limits.
Functions are abstract representations that map inputs to outputs according to specific rules. In calculus, functions allow us to study how quantities change relative to each other. For example, a function could describe the position of an object as it moves over time or the temperature at different altitudes. Continuous functions have critical properties that make them essential for understanding real-world phenomena. They ensure smooth transitions and allow us to find maximums and minimums within specified intervals. Discontinuous functions can present challenges, but are still valuable in modeling situations where abrupt changes occur, such as switching between different states or conditions. The concept of differentiability extends this idea by examining rates of change at specific points. A function is said to be differentiable if its derivative exists. Otherwise, it has a discontinuity. This allows us to approximate functions using tangent lines and understand acceleration in physics problems. Differentiability also plays a role in optimization, helping identify points where the rate of increase or decrease becomes zero. Implicit differentiation provides another powerful tool for finding derivatives without explicitly solving equations. By differentiating both sides of an equation with respect to one variable, while treating others as constants, we can uncover relationships between variables that aren't immediately apparent through standard methods. Continuity ensures that small changes in input produce correspondingly small changes in output, a property essential for describing physical systems. Continuous functions are characterized by their ability to be drawn without lifting the pen, meaning they don't have jumps or breaks. Understanding continuity is crucial not only for theoretical mathematics but also for practical applications like engineering design and data analysis. The intermediate value theorem, IVT, highlights a fundamental aspect of continuous functions. If you can draw a smooth curve connecting 2 points on a graph, then there must be at least one value within that range where the function takes every value between its endpoints. This theorem is widely used in proving existence results and has practical implications for solving equations numerically. In addition to IVT, we explore common types of discontinuities, removable, jump, and infinite, and how they affect a function's behavior. Discontinuities can occur at points outside the domain, but are important in understanding why some functions might behave erratically or exhibit sudden changes. Understanding these nuances helps mathematicians and scientists model complex systems accurately. Differentiability provides deeper insights into how quantities change by examining their rates of change through derivatives. Derivatives represent slopes of tangent lines at specific points on a curve, giving us precise information about local behavior. By analyzing these slopes, we can determine whether functions are increasing or decreasing and identify critical points where the rate changes. The chain rule is particularly useful when dealing with composite functions composed of multiple layers. It allows us to differentiate complex expressions by breaking them down into simpler components. This technique simplifies calculations in various fields, including optimization problems in economics and physics simulations. Taylor's theorem offers a way to approximate smooth functions using polynomial expansions. By expressing a function as a series centered around a particular point, we can estimate its value accurately over small intervals. This approximation becomes increasingly precise as more terms are included in the expansion, making it invaluable for numerical computations and theoretical analysis alike. The fundamental theorem of calculus, FTC, bridges two seemingly disparate concepts, the derivative and the integral, linking them through a deep mathematical relationship. It states that if f is an antiderivative of f on an interval, this theorem provides a method for computing definite integrals efficiently, while also ensuring the existence of antiderivatives. Its significance extends far beyond mere computation. It enables physicists and engineers to analyze quantities like work done by forces acting along paths or energy changes in thermodynamic processes. FTC has numerous applications, from solving real-world problems involving motion and force dynamics to abstract explorations into properties of functions themselves. Understanding this theorem opens up new possibilities for exploring more advanced mathematical structures, such as Fourier series and harmonic analysis.
In conclusion, this journey through functions has revealed their profound impact on mathematics and its applications. From laying the groundwork with the real number system to delving into advanced topics like differentiability and integration, these concepts form a cohesive narrative that enriches our understanding of both theory and practice. As we step back from these intricate details, it becomes clear that functions are not just abstract entities, but powerful tools for modeling and solving complex problems. Whether in physics, engineering, economics, or any other field, their ability to describe relationships between variables remains unmatched. The study of functions continues beyond this summary, inviting readers to explore further into the rich world of mathematics.